guys, so here we are at the water station, and what I want to know today is this water healthy? Well, first of all, healthy for what? Healthy for me a drink? I don't think I'm going to try that. So healthy for what? Healthy for the fish and the other animals. Absolutely. So is this water healthy for the fish and other animals? Wait a minute. You guys are scientists today. That means no guessing allowed. So we're going to be doing a number of different tests to determine whether or not our water is healthy. So let's see. The first thing we're going to be looking at is dissolved oxygen. Alrighty, so here we are down at the tidal creek, and we're going to be testing our dissolved oxygen concentration in the water here. Now, those of us that live up on land, we're in luck because the atmosphere is always about 21% oxygen, so we don't have to think about it. But down in the water, the fish and the other animals, they've got a little bit harder. Dissolved oxygen can change drastically throughout the day, and sometimes it can even get so low that fish will actually end up suffocating and dying. So we certainly want to keep an eye on dissolved oxygen. Now, one of the easiest ways to do it is with a handy dandy little meter such as I have here, and it's real easy to use. All I gotta do is put the probe down in the water. Alrighty, so all I gotta do is go ahead and stir the probe around in the water, and then our DO meter will give us our reading. And so it looks like we've got a DO reading today of 8.3 parts per million. Parts per million, that's a tiny, tiny little fraction. You guys are used to dealing with percents, that's parts per 100. But this is parts per million. In other words, if I could magically divide up a bucket of water into a million parts, only 8.3 out of a million would be oxygen. The majority of it would be water and salt and other things like that. So that's a tiny, tiny little fraction. Is that going to be good enough for our fish? Don't know. We got to consider what the fish are adapted to, what they're used to dealing with year after year. And the only way we're going to know that is by looking back over the historical area to find out what the usual conditions are out here in the marsh. So I look back on our historical record, and I find that back here in the marsh, the dissolved oxygen typically runs between 4 and 12 parts per million, with 8 being about average. But still, that's a pretty good level for the fish, and they should be happy with that. Now, it gets down below 4 parts per million, that's when fish are going to start getting stressed out. Gets down below 2 parts per million, that's when you're going to end up with some fish dying off and floating to the surface. Alrighty guys, so here we are down by the tidal stream, and we're going to be testing for pH. Anybody know what pH is? pH is a measure of the acid-base balance of a solution. And the pH scale goes anywhere from really acidic down towards the 0 end of the scale, all the way up to basic, which would be the 14 end of the scale. And if you had pure water, that would be perfectly balanced between its acids and bases with a pH of 7, or what we call neutral. Now, of course, easy way to test for pH, you may have seen one of these kits down at your local swimming pool, because of course we like having a pH that doesn't irritate our eyes. And real easy to use this kit. All you gotta do is go ahead and get yourself a water sample, and we'll shake it down to the line on the vial. And then this test relies heavily on what we call an indicator solution. Indicator solution changes color depending on the acid-base balance of that solution. So all I gotta do is take some of this reddish indicator solution, and I'm putting 10 drops in here. And we can go ahead and cap that back up. And I'll shake up the vial and cover it here. And you can see that reddish solution turns green in our vial. And is that good? Don't know. Gotta have something to compare it to, right? So what I've got to compare it to are these lab samples of a known pH with the indicator solution already added. So now all I gotta do is compare my sample to the lab samples. So it looks like it's over here on this side. I'll drop the vial in and hold that up to the light, and then I can just read if one of the numbers beside it look exactly alike. I can go ahead and just read the number off the scale here. And so it looks like we got a pH of 7.5 for today. 7.5. And so is that good? We don't know. Always got to consider what the fish are adapted to. So when we take a look at our historical record for this area, we find that the pH typically runs between 6.5 and 8.5. And so we're well within range. And it looks like our pH is good for today. Alright guys, so we're going to be looking at salinity. Anybody know what salinity is a measure of? That's a measure of how much salt is in the water. And of course, being in a salt creek, you'd expect to find some salt. So easy way to measure salinity is to go ahead and just take myself a sample of water, put it out there in the sunlight, and wait for it to dry out, and then I can weigh how much salt's left in the bottom. You think we got time for that today? I don't think so. So the way that we're going to be figuring out our salinity is through figuring out the density of our sample. Now when they set up the metric system, they decided to make life real easy on you guys. They decided that 1 cubic centimeter equals exactly 1 milliliter, and 1 milliliter of pure water weighs exactly 1 gram. 111. Doesn't get much easier than that, right? Okay, so if I had a bucket of pure water here, every milliliter of it would weigh exactly 1 gram. Now let's say I have something that's heavier than water. Salt. Salt's heavier than water, right? So let's say I added some salt to the water, slowly mixed it up so that it becomes part of the solution, and then take out a 1 milliliter sample. Now is that going to be heavier, lighter, or the same as the pure water? It's going to be heavier because salt's heavier and it'll make the solution heavier. And so let's try something else. Let's try a little bit of sugar. Sugar's heavier than water, right? I dump some sugar in there, I mix it up, take out a milliliter sample. Is that going to be heavier, lighter, or stay the same? It's going to be heavier as well. But do you think we got a lot of sugar out in the tidal creek? No. So go to figure, salt's usually what you find in Salt Creek. So what we're doing is we're making the assumption that the difference in density is due to salt, because salt's usually what you find. So here, let's try another one. Let's try sand. Sand's heavier than water, right? So I go ahead and I dump some sand in there, I mix it up, and then I go ahead and take out a milliliter sample. Is that going to be heavier, lighter, or will it stay the same? It stays the same, because the sand doesn't become part of the solution. It just sits on the bottom of the bucket. And so it's only those things that'll become part of the solution that'll affect the solution's density. Now the way that we're going to be measuring our density today is with a handy dandy little device here called a hydrometer. Nothing too fancy, just a float with a weight on the bottom, and then there's a little scale up here on the neck, and you can see right at the top is 1.000 grams per milliliter, the density of pure water. So if there was anything in that water that was making it more dense, it'll make it float a little bit higher, and then we can just read how much heavier that sample of water is than pure water would be. But wait, there's one more thing we got to take into consideration. You'll see that on the hydrometer, the technician back at the lab wrote at 75 degrees Fahrenheit. And he had to give us that little bit of information because, believe it or not, temperature can affect the density of our sample. I know that sounds kind of weird. Temperature affects how much each milliliter weighs. But think of it this way. If I had a hot air balloon and I fill it up with hot air, what's it going to do? It's going to float because the hot air is less dense than the air around it. Same exact thing with water. As it becomes warmer, it becomes less dense and it rises. As it becomes colder, it becomes more dense and it sinks. That's why if you're the first kid in the pool in the summertime, you'll ever notice that it's warm up near the top and cold down the bottom. That's that difference in density of the water layering it out like that. So the way that we measure with our hydrometer is we're going to go ahead and just put some of our water sample in our graduated cylinder here. Need a little bit more. And then I go ahead and I just let this float down into the column. But there's, and you can also see that we got a little temperature gauge in there, so we'll get in the temperature at the same time. So we'll go ahead and let that settle out. And let's see here. And we've got 1, 2, 3, 4 lines. So that's 1.004 is our hydrometer reading, 1.004, and that's grams per milliliter. And so now that I got that bit of information, I can go ahead and get our temperature. And it's looking like our temperature today is 82 degrees. So now that we got those two bits of information, we can go ahead and pull out our handy dandy little conversion chart. And you'll notice on the left hand side it says observed reading. I'm just going to slide down to 1.004, and then I look across the top and I find the temperature, and the temperature here is 26 degrees. So I just cross over from 1.004 to the 26 degree column, and we've got a salinity today of 7.9 parts per thousand. Now that's a tiny little fraction, parts per thousand. That's a fair bit larger than parts per million, but still real tiny. There's only a little bit of salt in that water. Is that going to be a good level for a fish? Don't know. Always got to consider what the fish are adapted to. Alrighty, so taking a look at our historical record, we find that we get a huge range of salinities out here in the marsh. Now, if I was back up into the freshwater creeks, we'd have a salinity below 1 part per thousand. And if we were out in the ocean, we could get up above 30 parts per thousand. But that mixture of fresh and salt water that we get back here in the bay and up in the salt marsh is what we call brackish water. So it's a huge range of salinities that we get back here. Are the fish going to be okay with that? Yeah, that's what they're adapted to. Alrighty, so our next parameter that we're going to be testing for is turbidity. Anybody know what turbidity is? That's a measure of how cloudy or how murky the water is. And so in order to do that today, we're going to be taking the kayak out into the tidal stream here to get a better measurement of our turbidity. Alright, so here we are out on the water. Beautiful day, lots of sun, lots of birds flying around. And I wanted to take a moment just to explain our high-tech equipment here. This is what we call a Secchi disc. And as you can see, it's just a weight on the bottom with a black and white plate, so it's easy to see. And then there's a line with a bunch of little marks on it. So the way that this works is as I go ahead and I just lower it down into the water until I can't quite see it. And then I bring it up, now I can just start to see it. And then I go ahead and I record how far down in the water I can see my Secchi disc. Today the water is looking kind of murky. I can only see down about a foot. But that's typical for back here in the marsh. Lots of algae, lots of sediments floating around. And so that can certainly affect that turbidity, affect how much we can see down into the water. Alrighty guys, so let's see, is this water healthy? Well, looks like we did pretty good on dissolved oxygen. Salinity is right about where we expect it to be. pH is where it's supposed to be. Are the fish going to be okay with that turbidity? Yeah, that's what they're adapted to. So turbidity is fine for those fish that are adapted to it out in the tidal creek. So it's looking like from the parameters that we measured today, the fish should be in good shape for another day.